All right. So let's talk a little bit about the double precision and about the single precision. All right. So as you said, uh, by default, and the data is saved as double, 8 bytes per element, as you see in here. So for example, if I type A, there's a variable A, it has one value, but the amount of bytes for this value is 8. So 1 times 8 total is 8. If you take a look at B, which has 10 elements, each element of this 10 stores 8 bytes. So 1 times 10, double. 10 times 8 will be 80 bytes. 80 bytes total. Alright? And that's by default how is by default it will be created as a double. If you would like to know what is the maximum value for a double in your computer, so just real max, sorry, uh, real max, all right, it will be 1.7977 to the power 308. That's the maximum value. If you'd like to know the minimum value, the minimum, which is minimum, real minimum, okay, real minimum, it will be 2.225 to the power minus 308. All right, anything above this will be considered infinity. Anything less than this will be considered zero. It becomes so small. So if you like to test it, let's create x, which equals to, let's say, 5 to the power 400. All right, because it's above this value, it was considered as infinity and saved in the workspace as infinity. So x in here, one element, is a double element, and it's stored, the value is infinity. Anything lower than the minimum will be considered as zero. So for example, 1 to the power, let's say, minus 400. All right, so it's saved as zero. So the value, as you see in x in here, became um, um, okay. So let me assign a value. Let me make it y just to see it. Y equals like this. Y. So y is one element. It's a double. It was stored in 8 bytes, and the value is zero. So you have to be aware of the limits. So there is something called single precision floating point numbers, and these single precision for floating point numbers use only 4 bytes, so half of the space, half of a space. If I create d, for example, equals 5, all right, d equals 5. Take a look at the d in here. It's double. By default will be created as double and allocates in the memory 8 bytes. All right, and the value is 5. Let me change it to a single. So if I say d equals, okay, a d equals single and 5. I use the function single 5. Now it's a single. Now it's a single. So when I look at the d now, it was stored in the memory and used only 4 bytes. 4 bytes. 4 bytes. All right. So it will save the space for you. If you'd like to know the maximum value for a single, so just real max and put here single. All right, and that's the maximum value for a single. Remember, the maximum value for double was plus 308. Here only 38. If you like to know the minimum also, you could say minimum for the single. All right, and that is the minimum value. So you have to be careful. You have to be careful. Mostly nowadays, because computers are like advanced, and I mean, like, they have a huge memory, you don't have to replace double with a single. But also, it could improve the run time of a long problem by changing from double to single precision. So that will be useful in some application. So let's create some series. So let's say n equals 1 to 10. All right, so n, as you see in here, it has 10 elements, 1 2 3 up to 10. And because each element is double times 1 double times 8 will give you 80 total storage in the memory. So let's create the harmonics. The harmonics, which is harmonic, equals, we take the value divided by the n. Okay, divided by the n. Again, the harmonic in here is like 10 elements and stores in the memory 80 bytes. All right, if you would like to take a look at it in a nicer way, you could say a harmonic. This harmonic. So these are the values. These are the values. So the first value is 1 over 1. All right, 1 over 1. The second value, 1 divided by 2, will give you half. The third one will be 1 divided by 3, will give you 0.333. The fourth one, it will be 1 divided by 4, will give you 0.25, up to the last value, which is 1 divided by 10, will give you 0.1. All right. If this is not clear to you, so change the format as we learned before, rational, and now type it, harmonic. Okay, so it's 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, 8, 1 over 9, 1 over 10. Just this is like a different view, like a different view. All right, short. Okay, so you could change it back to short. So short. All right, and you could display it again as you wish. Harmonic. This is short format, and this is fraction block format. All right, so let me clear the screen a little bit in here. Okay, I'm just clearing this cleaning the screen, but I'm not clearing the values. You see the values are, make sure you don't use a clear. If you use a clear, it will clear everything. It will clear the memory. So if we need to have cumulative sum, like we're adding all the values in the vector, okay, there's a function for that. So let's call it partial sum equals uh, cumulative sum for the harmonic. Here you go. So it will add all the previous elements. So start with 1, then 1 plus 1, then 1 plus half, 1 and a half, 1 plus 1/2 and 1/3 will give you this value, up to the total sum will be here 2.9290. This is we call the cumulative sum. So n will becomes as we go becomes smaller and smaller and smaller, because you are dividing by n, dividing 1 by n. So if you consider a bigger, let's try to consider a bigger number. Clean actually CLC. I'm gonna clear it now. CLC. Let's say n now equals to 1 to to 7,000. Let's say okay, to like a million values. Okay, so 1. Okay, to let's say 1 to 1 e 7. All right, so this is a huge array. Let's take a look at n now. How much? So n, and has 1 next to it, 7 zeros. 1 2 3 7 zeros. That means 10 million. This vector has 10 million values. 10 million values. 10 million values. All right, let's do the same thing. Let's calculate the harmonics. Okay, the harmonic, which equals to 1 divided by n. All right, and let's also calculate calculate the partial sum or the cumulative sum. So let me call it partial sum, which equals to cumulative sum for the harmonics. There you go. So when you look at the harmonic in here, where is the harmonic? Okay, it's again, it's 10 million elements, 10 million elements, and look how big is the size in here. How big the size in here. All right, let's say let's plot it. I mean to show you the plot. All right, for partial sum. All right. So that is the plot for the partial sum. So you have in here how many elements? You have, you know, 10 million elements. 10 million elements, and you plotting it, and that's the shape of it. All right. So now let's change it. Let's hold on this graph and change the values, okay, to a single. So n we'll take this in here and copy, and let me say v, but now I will make it as a single, not double. As a single, not a double. All right. So look in here before I run this, n, how many n? It has like 8 million, 80 million. It has like 80 million bytes. 80 million bytes. When I change it to single, it will be half. So let's take a look at n. Now it's a 40 million. 40 million. Let me calculate also the harmonic, the same thing. I'm gonna do the harmonic, the same thing. Copy in here. I'm gonna paste it in here. Same thing. All right. And let me calculate also the partial sum. The partial sum in here. We'll say copy. Okay. We'll say paste. Same thing. The only difference now I'm using single. And let me say hold on. So I'm gonna keep the previous graph. Now I'm gonna graph it again. Let me graph it, plot it again. The plot again. I'm gonna plot it again. Copy. All right. And just to look different, I will change the line format. Let's make it different line format like that. All right. So enter. All right. Let me take a look at the figure. Where is the figure? It's in here. So this is the first graph. Kept going up, and this is the second graph. As you see in here, it became steady sooner. The reason for that, after a certain value, it will become all zero. It will become zero. There is no change in the value, so it does not add anything to the value. So which one is more accurate? The blue one. Which one is less accurate? The orange one. However, you know, this will consume much more less memory than this one. All right. So that's the double and double precision and single precision. All right. There is also integer. Let me talk about the integers very quickly. So if you like to have, first of all, for integers, all right. Let me show you the integers in here. Okay. So there's 8 types of integers. There's single 8-bit single integer, 16-bit single integer, 32-bit single integer, 64 bits. I'm sorry, signed integer. So signed, all of these are signed integers. That's how are the functions, and it's 8, and it's 16, and it's 32, and it's 64. Also, mirror to that, we have the unsigned ones. So let's take a couple of examples quickly. Let me clear this from my way. And E, let's create E now. Now E, I don't need it to be double. I don't need to be single. I need it to be integer only. So integer 8, all right? And let's say the value is 10, all right? So integer 8 and the value is 10. So let's take a look at the E value. As you see in here, E, one element. The type is not double, is not a single. It's integer 8, and integer 8, it will have 1 byte storage, 1 byte storage, and the value is 10. So it saves only in integers. Would you like to know what is the maximum value for the integers? So just say integer max, all right, and init 8, close this like that, and it's 127. So the maximum value you could save in integer 8 is 127. All right, so let's try to do this. Okay, E, let's try to do E again, copy here. But now we need to assign it a value 200. Okay, so it gave it only 127 because that's a maximum. So you have to be very careful. You have to be very careful with the limits. All right. Um, for the unsigned, okay. So let's repeat this in here to know the integer max for the unsigned. Copy, Control V. Okay, and this is we'll use it for the unsigned integer. Unsigned integer 8, and the maximum value is 255. Remember, the unsigned variable could only save or store for you a positive numbers. All right. For the complex numbers, so for example, let me clear this. Okay, say f equals to, let's say, 5. As you know, it has two parts. Complex numbers has two parts, 3i, for example. All right, so it has two values. So the default storage type for complex numbers is a double. Let's take a look at the f in here. The f is one element. Double, it tells you is a complex, double complex. Okay, and because it's two values, 8 byte and 8 bytes, so it totals 16 bytes, and that's the value. So the default is a double. However, it was as much the storage room because we have two numbers, one integer and one real and one imaginary number. All right. So it will be 16 bytes. So the complex numbers will need 16 bytes. Okay, which is about 28 bits to save that number. All right. Complex numbers also can be stored as singles or integers. Okay, as singles or integers, you could do that. So you could, for example, say G, all right, equals init 8, all right, and the same value 5, for example, 5 plus 3i, all right, yeah, 3i. Okay, so I forgot in here to put the parentheses. So all right, so this is saved as an integer, and it will be like 4 plus it will be 1 plus 1, which is 2. Let's take a look at G in here. Where is G? Okay, one element is a complex and has 2 bytes. So sometimes you need to watch your memory usage, especially in huge applications, and it's a good thing to be aware of the different types that MATLAB supports you with.